Hey, Dr. Clark coming at you with a Check Your Understanding video. We're in section 7.3, which is more Laplace transforms here using translation rules. For this problem, they've given us a spring mass damper setup with a mass of 1 kilogram, friction proportional to velocity with constant 7, and a spring with spring constant 6. A rightward force of 30 newtons is applied for t between 0 and 3 and then removed. The mass is released from rest at equilibrium position. Write the initial value problem that models the scenario and then use the method of Laplace to find the solution. Okay, so the standard spring mass damper model is this. mx double prime plus bx prime plus kx equals f of t. In this case, the mass is given as 0, so we have x double prime. The friction is proportional to velocity with constant 7. Well, this is proportional to velocity, so that's 7x prime. And this is your spring force, and they said the spring constant is 6, so we've got x double prime plus 7x prime plus 6x. The forcing term is given as follows. It is for 3 seconds a force of 30 newtons, a constant force of 30 newtons, and then drops off thereafter. So it's 30 newtons and then nothing. The key to this problem is writing that using the unit step function. So that is 30 newtons, and then we're going to subtract 30 u t minus 3. So starting at 3 seconds, this goes from 0 to 1. When this becomes 1, 1 times 30 is 30. 30 minus 30 is 0. So this starts at 0, which means we're at 30. Then at 3 seconds, this jumps up to 1, which means 30 minus 30 is 0. So it gives us exactly the unit step function we're asking for there. Or the unit step function gives us the forcing term that they're asking for. And that's a differential equation. An initial value problem would have initial conditions. In this case, position of 0 and velocity of 0, because it said it was starting from rest, which means velocity 0, at equilibrium, which means position 0. So that is part A. For part B, we're going to use the method of Laplace. So we're going to Laplace transform the entire equation. So we have L of x double prime. I'll use the linearity of the Laplace transform to split out the terms here. And then I'm going to use our formula that L of x prime is S L of x minus x at 0. That is using Laplace to convert derivatives to remove, basically remove derivatives. That's kind of the power of Laplace. I'm assuming you're familiar with that. When we do that, we're going to get what? This will be S L of x prime minus x prime of 0, but that's just 0. B was given as 7, so we have 7 times S L of x minus x of 0, but that was given at 0. And plus k, which is 6. I guess that's just L of x. Well, maybe I'll just write that here. 6 L of x equals, and then maybe underneath here we can write L of 30. So L of 30, that's a constant. So I think I put a couple ones down here. Well, L of 30 is just 30 over S. That's L of 30. And then we're going to have minus 30. This is going to be e to the minus 3s over s. So using the linearity, we can just factor out the 30. What is ut minus 3? So I included that one down here. u t minus 3 is e to the minus 3s over s. Okay, that's the Laplace transform of u t minus a. All right. And then we can, I guess, do this one more time. We'll get s times s L of x minus x of 0, but that is just going to be 0 from the initial conditions, plus 7s L of x plus 6 L of x equals 30 over s minus 30 e to the minus 3s over s. And so in the end, we're just going to get L of x factored out, multiplied by the characteristic equation, s squared plus 7s plus 6 equals 30 over s minus 30 e to the minus 3s over s. And L of x, therefore, will equal 30 over... Oh, and I think this is overdamped, and that can be factored. So I'm going to divide, I think it's s plus 6, s plus 1. So when we divide this quadratic down here and down here, I'm just going to factor it into its two constituent parts. Minus 30 e to the minus 3s over s times s plus 6 times s plus 1. All right. Now, in order to find x, we will have to apply the inverse Laplace transform to right-hand side. That's not going to work with this unless we decompose this into linear terms. So we're going to need to know, and we have to use partial fractions to do that. So let me copy this here. And one way to do partial fractions is to just go to Wolfram alpha and say, Wolfram alpha, please put this thing into partial fractions, and it will say, oh, boom, 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 and it will do it for you. Now, we can do this by hand, so let's do it by hand just to see that, that we can, in fact, do it by hand. And so the idea here would be this is going to equal a over s plus b over s plus 6 plus c over s plus 1. If we multiply everything by the denominator of the left-hand side, then that side removes to 30. On the a term, the s will cancel and will leave us with s plus 6, s plus 1. On the b term, the s plus 6 will cancel and we'll get just, I guess, s plus 1. And on the c term, the s plus 1 will cancel and we'll get s times s plus 6. And the easiest way to do this is to first say if s is equal to 0, this term and this term are going to be 0. And we will be left with 30 equals a times 6, because 0 plus 6 is 6, 0 plus 1 is 1, 6 times 1 is 6. And that means that a must be 30 divided by 6, which is 5. So a can be started to be 5. For this term, we can set s equal to negative 6. And if s is negative 6, this term and this term are going to cancel to 0. And we're going to be left with 30 equals b times, well, whatever negative 6 times negative 5 is. Negative 6 times negative 6 plus 1, that's 30. And b must therefore be 1. And for c, we can set s equal to negative 1. And then that will cancel this term and this term, and you'll be just left with 30 equals c times negative 1 times 5, which means that c is, what, negative 6? Okay, and that is exactly what we got here, right? Negative 6, 1, and 5, the same numbers as Wolfram alpha. Okay, So going back to our original problem then, the original problem said that L of x was equal to this, 30 over s plus 6, s plus 1. But that is then equal to a over s, so 5 over s, plus b over s plus 6, so 1 over s plus 6, plus negative 6 over s plus 1. And that accounts for this right here. But this one is exactly the same. It's the same 30. It's just negative, and it's multiplied by e to the minus s. So what we can do is we can subtract this same thing and just multiply by e to the minus 3s. Okay? So if we also write down plus, well, I guess we could write down minus e to the minus 3s times the self-same 5 over s plus 1 over s plus 6 plus negative 6 over s plus 1. And we can then find x of t by applying the inverse Laplace transform to right-hand side. And that is going to be, well, let's see. First we have 5 over s. When we inverse Laplace transform that, we're just going to get 5. We're going to have 1 over s plus 6. That's just going to be e to the minus 6t. And then we have negative 6 over s plus 1. That's just going to be negative 6 e to the minus 1t. And that is essentially the solution responding to this force right here. And you can see if the force is 30, and 6x equals 30, then x equals 5. That's the particular solution. And the homogeneous solution is going to be related to the characteristic equation, some combination of e to the negative 6t and e to the negative 1t. That's showing up right here, e to the negative 16, e to the negative 1t. And the initial position is 0. Here's 5 plus 1 minus 6 is 0. And the initial velocity is also 0. This will give you negative 6 plus 6 equals 0. So we have, from here, the initial condition set. We've got a particular solution. We've got a homogeneous solution. But then, all of a sudden, the power turns off. And so we need to respond to that change. And that is what e to the minus 3s is doing for us right here. So e to the minus 3s is going to essentially take whatever we would normally get and shift it and turn it on at that time, at 3 seconds. So when any term that has the e to the minus 3s, we should expect to have a unit shift function and the basic function shifted by 3 units. Okay, so plus, so this e to the minus 3s means we're going to have a unit shift function of 3 seconds. I guess they're all minus, so I might as well just put minus out front. Multiplied by, well, so 5 over s, the basic function that comes from is just the constant 5. And if you shift a constant, nothing happens. This would be an e to the negative 6t. So we need an e to the negative 6 parentheses t minus 3. We have to shift it so that it turns on at the same time as the u function. And then minus 6 e to the minus 1 parentheses t minus 3. Again, we have to take negative 6 e to the minus 1t, but shifted it to match the unit step function. And so that is the complete solution to that problem. It's a fair bit of work, but if you can get that, you should feel pretty good about your understanding of Laplace transforms with more difficult forcing terms. We'll see you next time.